Zorn's lemma states that in a partially ordered set, if every chain has an upper bound, then the set has a maximal element. What? When I first saw this lemma, it made no sense to me. What is this lemma actually saying? Why should we talk about it? Is it ever useful? I feel like I'm not alone in this confusion. Outside of advanced math textbooks, the only times I see Zorn's lemma mentioned are in jokes about how confusing it is, or when people are talking about things that are equivalent to the axiom of choice. If you don't believe me, look at the Wolfram Math World page for Zorn's lemma. It states the theorem, says it's equivalent to the axiom of choice, then makes a couple of bad jokes about it. However, in reality, Zorn's lemma is a very interesting and useful result for producing large mathematical objects, and relegating it to jokes and obscure proofs is doing it a huge disservice. In this video, I am going to try to dispel this confusion about Zorn's lemma and get at the heart of what it's saying and how to use it. To do this, I am going to start by looking at several different problems. While we won't be able to solve them right away, trying to solve them will reveal that the solution to each problem is very similar. Generalizing this solution strategy will lead to the statement of Zorn's lemma. Before proving Zorn's lemma, we will first see how to solve the original problems using it, and then we will finish by proving Zorn's lemma itself. So, the first problem we will be looking at is finding bases for vector spaces. A basis for a vector space is a linearly independent spanning set. In simple vector spaces like the 2D plane, it's easy to find a basis, such as this one. However, what about bigger vector spaces, like function spaces? It's much harder to visualize this. The question then becomes, does every vector space have a basis? This is a problem that we'll solve by using Zorn's lemma. Let's try to figure this out. Consider an arbitrary vector space. Let's try to build up a basis step by step. First, let's pick a random non-zero vector and consider the set containing just this one vector. This set is linearly independent, so it's possible that it's a basis. If it is a basis, then we're done. If it's not, that means there must be a vector not in the span of this set. Because it's not in the span of the set, we can add it to the set, and this new set will be linearly independent. Thus, it's again possible that this new set is a basis, so we can repeat this process. If it's a basis, we're done, and if it's not, we can add another vector to the set. We can keep repeating this process until eventually, we run out of vectors to add, and we have a basis. Now you might object to this and say that some spaces have infinite bases. However, this process works indefinitely, well past infinity. Even if we have to repeat the process infinitely, it must eventually end. Now you might still object to this, saying that repeating a process infinitely is impossible, and well, you're right. This is the gap in the proof that we'll need Zorn's lemma to prove. However, if we can fill this gap, the proof is complete. We keep repeating the process until we get a basis. The next problem we will be looking at is related to orders. We have many elementary examples of orders, such as the order on the natural numbers, the order on the integers, the order on the rational numbers, and the order on the real numbers. Some things that all of these orders have in common is that every number is less than or equal to itself, every two numbers that are less than or equal to each other are equal, A being less than or equal to B and B being less than or equal to C implies that A is less than or equal to C, and for any two numbers, one is less than or equal to the other. To generalize the concept of orders, we say that any relation on any set that satisfies these conditions is a total order. While most of the orders that we first learn about are total orders, there are other kinds of orders. One of these is to remove the last condition, which creates something called a partial order. While every total order is a partial order, there exist partial orders that are not total orders. The archetypical example is the subset relation, where we say that one set is less than or equal to another if the first is a subset of the second. One interesting thing that can happen in partial orders is that we can have things that are incomparable. For example, neither of the sets containing just 1 and just 2 are less than the other. While they may seem strange at first, partial orders are ubiquitous throughout mathematics. Another kind of order is well orders. Well orders are the same as total orders with the added condition that every non-empty subset has a least element. It's actually pretty hard to make a well-ordered set. In fact, out of all of the commonly known ordered sets, the natural numbers are the only one that is well ordered. Even the integers with their usual ordering aren't well ordered because the set of integers itself has no least element. However, even if the usual ordering on the integers isn't a well order, what if there's a different order on the integers that is a well order? For example, we could take all the negative numbers and reverse them. This new ordering on the integers is, in fact, a well ordering on the integers. Of course, by doing this, we are no longer talking about the usual ordering on the integers. The important point is that there exists some order on the integers, no matter how different from the usual order, that is a well order. What about the rational numbers? Is there some way we can well order the rational numbers? The rational numbers are dense in their usual order, so this may seem impossible. However, consider this. Let's first list all of the positive rational numbers with a denominator of 1. After this, let's list all of the positive rational numbers with a denominator of 2, skipping any that we already have. After this, let's list all of the positive rational numbers with a denominator of 3, skipping any that we already have, and so on. After going through all of the positive rational numbers like this, we can repeat the process for the negative rational numbers. After doing all of this, we still haven't included 0, which we can just tack on at the end. Believe it or not, this is actually a well order on the rational numbers. So we see that even if it might get complicated, a lot of sets can be well ordered. The natural question at this point is, can every set be well ordered? This is a problem that we'll solve by using Zorn's lemma. Let's try to figure this out. Consider an arbitrary set. Let's try to build up a well ordering step by step. First, let's pick a random element and say that this is the least element of the whole set. If the original set happens to be just this one element, then we're done. If it's not, that means there must be another element. We can extend the ordering by saying that this new element is greater than the first one. On this subset containing these two elements, this ordering is a well order. If this happens to be all the elements in the original set, we're done, and if it's not, we can add another element on the end. We can keep repeating this process until eventually we run out of elements to add, and we have a well ordering on the entire set. Now you might object to this and say that some sets are infinite. However, this process works indefinitely, well past infinity. Even if we have to repeat the process infinitely, it must eventually end. Now you might still object to this, saying that repeating a process infinitely is impossible, and well, you're right. This is the gap in the proof that we'll need Zorn's lemma to prove. However, if we can fill this gap, the proof is complete. We keep repeating the process until we get a well ordering on the whole set. The last problem we will be looking at is related to field extensions. A field extension of a field is another field that, in a certain sense, contains the first field. One common method of producing field extensions is taking the ring of polynomials over the field and then finding the quotient of this ring with the ideal generated by an irreducible polynomial. This produces a field extension of the original field that includes a root of that polynomial. Now, if you haven't taken an abstract algebra class before, a lot of this might be unfamiliar, but the important point is this. Given a field and an irreducible polynomial in that field, we can construct a bigger field that includes a root of that polynomial. For example, starting with the rational numbers and the polynomial x squared minus 2, we can construct a field extension that includes the square root of 2. Note that by doing this, we have defined the square root of 2 without ever mentioning the real numbers. Can we use this process to describe any real number? Well, this particular process works for algebraic irrational numbers, but not for transcendental numbers. However, there exist transcendental field extensions as well, by using rational functions. Again, the details of this aren't important here, but the main point is that it's possible to extend the rational numbers by any transcendental number without appealing to the real numbers. Now you may object to this by saying that we can't describe the transcendental numbers to extend with without having the real numbers in the first place, but we can describe transcendental numbers as gaps in the rational numbers. This idea allows us to describe transcendental numbers without having to find the real numbers. Thus, we can extend the rationals with any irrational number without mentioning the real numbers. Using these ideas, let's try to construct the real numbers from the rational numbers. This is a problem that we'll solve by using Zorn's lemma. Starting from the rational numbers, let's try to build up the real numbers step by step. First, let's pick a random irrational number. We can do a field extension to make a new field containing the rational numbers and this irrational number. If this new field has no gaps, then we're done. If it does have gaps, that means there must be another irrational number we haven't covered. Then we can create a new field by doing another field extension with this gap. If this new field happens to have no gaps, we're done. And if there is a gap, we can do another field extension. We can keep repeating this process until eventually we run out of gaps, and the result is the real numbers. Now you might object to this and say that we would have to do this infinitely to add all of the irrational numbers. However, this process works indefinitely, well past infinity. Even if we have to repeat the process infinitely, it must eventually end. Now you might still object to this, saying that repeating a process infinitely is impossible, and well, you're right. This is the gap in the proof that we'll need Zorn's lemma to prove. However, if we can fill this gap, the proof is complete. We keep repeating the process until we get the real numbers. Now that we've looked at these three problems, let's try to generalize this solution strategy. In each case, we were trying to build a large object by starting with a small object and iteratively adding to it until we couldn't add anything else. We can generalize this by considering each step to be producing an abstract entity rather than something in particular. But once we've started to consider these things as being abstract entities, how can we say that we're constantly producing bigger objects? Well, bigger makes me think of ordering, so let's assume we found some way to order these abstract entities. Note that often, these are not normal orders. In the three cases we looked at, we would have to find an ordering on linearly independent sets, an ordering on well orders of subsets, and an ordering on fields. In fact, the ordering on linearly independent sets is one which we've already seen before, the subset relation. Recall that this is a partial order, so in general, Zorn's lemma applies to partial orders. However, the neat thing about this process is that because we are chaining together bigger and bigger elements, the elements we are using to build up the big object are actually a totally ordered subset. Because chaining these elements together like this in a partial order produces a total order, let's call any totally ordered subset of a partial order a chain. At this point, we can start to work towards the statement of Zorn's lemma. Starting with the partially ordered set, we're trying to make a biggest element. But what do we mean by a biggest element? Well, normally we formalize this idea by saying that everything else in the set is less than it. This kind of element in a set is called a maximum element. However, this is not the kind of biggest that we are looking for. For example, going back to when we were proving that every vector space has a basis, in 2D space we might end up with the basis E1, E2. However, the set containing just E1 plus E2 is not a subset of this basis. Thus, bases are not maximum linearly independent sets. Instead, what we know is that we can't make any linearly independent set that's bigger than this one. The definition is slightly different, but this is the kind of thing that Zorn's lemma gives us. We call something that satisfies this condition a maximal element. While maximal elements and maximum elements are the same thing in totally ordered sets, they are distinct concepts in partially ordered sets. So it seems that Zorn's lemma states that every partially ordered set has a maximal element. But the problem with this statement is that it's wrong. The natural numbers are a partially ordered set, but they have no maximal element. Thus, there is still some condition missing from the statement of Zorn's lemma. To find it, let's look back at how we tried to solve our previous problems. We started by chaining together objects one by one. This step is valid in any partially ordered set. Then, we later asserted that even after chaining together an infinite number of objects, we could still find something bigger. This is the step that fails in the natural numbers. To be able to do this step, we must know that every time we have chained a bunch of objects together, even infinitely, we can still find something bigger than everything so far. Or in more formal language, every chain must have an upper bound. With this new condition in hand, we can finally state Zorn's lemma. In a partially ordered set, if every chain has an upper bound, then the set has a maximal element. Now that we've managed to state Zorn's lemma, let's assume it's true for the moment and use it to solve our original problems. This turns out to be a bit more confusing than it initially seems, so I want to spend a bit of time here talking about how to use Zorn's lemma itself. We want to use Zorn's lemma when we are trying to build up a large object. Our original idea was that we start with a small object, come up with a way to extend the object in individual steps, and find a way to continue the process after infinite steps. When utilizing Zorn's lemma, these steps all move around. First, we need to identify our partially ordered set of objects. This step can be surprisingly complicated at times. Next, we need to prove that every chain has an upper bound. This step mostly corresponds with the infinite step on the left. Then, Zorn's lemma gives us a maximal object, and we need to use this maximality to prove that it satisfies whatever property we wanted it to have. Usually, this is done with a proof by contradiction, where we assume it doesn't have that property, which allows you to find a bigger object contradicting the maximality of the object. In doing this, you have to do a single extension, meaning that this step actually corresponds to this earlier step on the left. This process on the right is pretty much how we solve problems using Zorn's lemma. But what about the starting step on the left? Is it actually not necessary? Well, when proving that every chain has an upper bound, we need to account for the empty set, because the empty set is a chain. Since any object is an upper bound of the empty set, finding an upper bound of the empty set is the same as finding a starting object. Thus, finding a starting object is also part of proving that every chain has an upper bound. However, sometimes the proof we use for every chain having an upper bound happens to work for the empty set without modification, so whether or not we need to explicitly find a starting object depends on the situation. Now that I've shown how Zorn's lemma is actually used, let's apply it to our original problems. Because this is a video about Zorn's lemma and not a video about algebra or set theory, I don't want to dwell on all the nitty-gritty details of the following proofs. What I want you to get out of these proofs is the way that they use Zorn's lemma, not how they do everything else. Thus, I will be moving quickly through a lot of the details of the proofs for the sake of time and understanding. So don't worry if you can't keep up with some of the details, since they are not that important for this video. Our first problem was proving that every vector space has a basis. The first thing we need to do is identify our partially ordered set. When trying to solve this problem without Zorn's lemma, we were building up linearly independent sets such that each one contained all the elements of the previous one. Thus, our partially ordered set here is the set of all linearly independent sets ordered by the subset relation. Now that we've identified our partially ordered set, we need to prove that every chain has an upper bound. So let C be a chain of linearly independent sets. What is an upper bound of this chain? Well, we just need to find a linearly independent set that contains all of the sets in our chain. The simplest set that contains all sets in a set of sets is the union of those sets. In this case, the union works as our upper bound. You do have to prove that the union is linearly independent, but that's not too difficult. In general, when using Zorn's lemma, if your partial order is the subset relation, there's a good chance that when proving that every chain has an upper bound, you can use the union of the chain. Since this union is the upper bound of the chain, we have now proved that every chain has an upper bound. So by Zorn's lemma, we have a maximal linearly independent set B. B being maximal means that there is no other linearly independent set that contains it. Now we need to use this maximality to prove that B is a basis. Like I said before, we will prove it by contradiction. So assume that B is not a basis. This means that there is some vector v that is not in the span of B. Thus, if we add v to B, we would get a linearly independent set containing B, which contradicts the maximality of B. Thus, B must be a basis, so we have now proven, using Zorn's lemma, that every vector space has a basis. Let's move on to the next problem, proving that every set can be well ordered. The first thing we need to do is identify our partially ordered set. When trying to solve this problem without Zorn's lemma, we were building up well orderings on subsets such that everything in a later subset was greater than everything in an earlier subset. So what's the partially ordered set here? There are subsets involved here, but the subset relation doesn't describe the way we are extending the well orders. Each step in this process seems to involve a combination of the subset and the way we order it. If both are important, why don't we just make our partially ordered set be a set of pairs, where the first part of the pair is a subset and the second part is the way we well order it? However, how can we partially order a set of pairs? Let's figure this out. If we have two of these pairs, we need to figure out a way to say that one is less than or equal to another. First, the first subset must be a subset of the second subset. Then to express that the order in the second pair extends the order in the first pair, let's say that if one value is less than or equal to another in the first pair, it is also less than or equal to the other in the second pair. Now we actually need one more condition here. In each step of making a bigger well order, we are extending the order by setting any new value greater than all the old ones. Thus, we need to add the condition that everything that is only in the second pair set is greater than everything in the first pair set. Believe it or not, these conditions do make a partial order on this set of pairs. Now that we've identified our partially ordered set, we need to prove that every chain has an upper bound. So let C be a chain of these pairs. What is an upper bound of this chain? Well, we just need to find a well-ordered subset that extends the order of all of the orders in our chain. The first part of the pair should just be the union of all the sets in the chain for the same reasons as in the previous proof, and the well order on this set can be made by borrowing the order from any of the sets in the chain. This pair is an upper bound of this chain, so we have now proved that every chain has an upper bound. Thus, by Zorn's lemma, we have a maximal pair. It being maximal means that there is no other subset with a well ordering that extends this one. We need to find some well ordering on the whole set from this. To do this, I will show that the set W is, in fact, the whole set. I haven't named the set we're working with until now, so I'll call it A. We will need to use maximality to prove this. Like I said before, we will prove it by contradiction. So assume that W is not equal to A. This means that there is some value C not in W. Because it is not in W, we can make a well order on the set containing C and everything in W by saying that C is greater than everything in W. This well order extends the well order on W, which contradicts the maximality of W. Thus, W equals A, which shows that the well ordering on W is a well ordering on A. Thus, we have now proven, using Zorn's lemma, that every set can be well ordered. The last problem we looked at is constructing the real numbers. Now, it turns out that when you formalize this one, you run into several issues that make the construction significantly more complicated. It is possible to work around these issues, but going through their solutions would take way too much time here when that's not the focus of the video. Instead, just for the sake of the video, I'm going to pretend these issues don't exist. The general idea behind the construction still holds, and seeing the general idea shows how Zorn's lemma is used more clearly. If you want to see all the details, I've written a document that goes through the entire construction that I'll link to in the description. So before you comment and say that a step in this proof doesn't work, look at that document first. Now let's construct the real numbers with Zorn's lemma. The first thing we need to do is identify our partially ordered set. When trying to solve this problem without Zorn's lemma, we were building up fields such that each one was an extension of the previous one. Thus, it seems that our partially ordered set here is all fields. However, the problem here is that there exist fields that are extensions of the real numbers, such as the complex numbers, so all fields is too general. We need to find some subset of fields where the real numbers are maximal. You might think that ordered fields would work, but there exist ordered fields that are extensions of the real numbers as well, so that won't work either. The issue with all ordered fields is that you can still have infinite elements that are greater than any natural number. So what if we restricted ourselves to Archimedean ordered fields, which are ordered fields that don't have infinite elements? This will finally work. But how can we order Archimedean ordered fields? Let's figure this out. You may think that the subset relation will work here, but in general, algebraic structures can be made on whatever sets we want, and asking if one is a subset of the other doesn't really describe what we're trying to describe. Instead, we can order these fields by checking for the existence of a homomorphism between the fields. In particular, we will check for a function that satisfies these conditions. If such a function exists, we say that one Archimedean ordered field is less than or equal to another. We also say that the first field can be embedded into the second. Now that we've identified our ordered set, we need to prove that every chain has an upper bound. So let C be a chain of Archimedean ordered fields. What is an upper bound of this chain? Well, we just need to find an Archimedean ordered field that has all the others in the chain embedded into it. While conceptually we would want to use a union again, we can't do that here because we aren't actually sorting by the subset relation. Instead, we can use the disjoint union of all the fields in the chain, and then set elements of this union equal to each other if they are equal under some homomorphism between the two fields that they are from. Formalizing this idea gives us an upper bound to our chain. But wait, an Archimedean ordered field needs operations too. Well, we can just borrow the operations from things in the chain. We also need a 0 and a 1, which we can get by picking any of the fields in the chain and using the 0 and 1 from that field. But this won't work if the chain is empty. This is one of those situations I mentioned before where we have to treat the empty chain as a separate case. Thankfully, the solution here is simple. If our chain is empty, we already know that the rational numbers are an Archimedean ordered field, so they are an upper bound of the chain. We have now proved that every chain has an upper bound, So by Zorn's lemma, we have a maximal Archimedean ordered field R. R being maximal means that there is no other Archimedean ordered field that R embeds into. Now we need to use this maximality to prove that R is complete. Like I said before, we will prove it by contradiction. So assume that R is not complete. This means that there is some gap in R, that is to say, a set of real numbers that has an upper bound but no supremum. While it's actually more work than I initially let on, we can do a field extension to fill this gap, giving us a bigger Archimedean ordered field in which R embeds, which contradicts the maximality of R. Thus, R must be complete, so we have now proven, using Zorn's lemma, that the real numbers exist. Now that we've seen how Zorn's lemma is used, let's finally prove the lemma itself. Now, while the proof itself is actually pretty simple, the ideas leading up to the proof can be a little confusing, so don't worry if you don't understand everything. Honestly, you don't even need to know the proof of Zorn's lemma to use it, and I'm mainly including this here for the sake of completeness and because I think the proof is cool. And if you're on the other end and want to see the proof in more detail, I've linked to the paper where I got this proof from in the description, although I've made a few modifications. And if you're really hardcore, I formalized this proof in a proof assistant, which I'll link to as well. Anyway, to work towards the proof, let's look back at how we intuitively were solving the previous problems. We were building up our maximal object iteratively, possibly infinitely, using the upper bound of any infinite chain. The problem is that we can't make an infinite chain in this way because it would involve repeating this process infinitely. We need to find a way to describe this process in a slightly different way that will allow us to talk about all of the objects we can possibly make in this way without ever invoking any kind of infinitely iterative process. The first step will be to formalize the method we use to build up chains. Even though it's not strictly necessary, we can use the language of chains and upper bounds for the single extension steps too, which can make things simpler. However, to ensure that we are actually extending the chain, we need to make sure we are finding a strict upper bound of the chain, not just a normal upper bound of the chain. As long as we haven't found a maximal object yet, a strict upper bound will always exist. To formalize this, let's define a function f whose domain is all chains with a strict upper bound, which takes each chain to such an upper bound. Something interesting about this function is that because it only accepts chains that already have a strict upper bound as input, its definition doesn't actually depend on the condition that every chain has an upper bound. In fact, until the end, this proof won't use that condition, and up until that point the proof will be valid for any partially ordered set. With this function, we can describe our process a bit differently. We start with some value a1, and then if it is not maximal, we apply f to the set containing a1, producing a new value a2. If it's not maximal, we apply f to the set containing a1 and a2, producing a new value a3. Actually, we can define a1 in terms of f as well. The empty set is a chain and has a strict upper bound as long as our set is non-empty, so we can define a1 as f of the empty set. Conceptually, we can continue this process of defining the next object as f of the previous objects until we hit a maximal object, but we still have that annoying issue of doing something infinitely. To try to get around this issue, consider each of these sets that we are applying f to. Is there some kind of characterization of these sets? Consider an arbitrary one of these sets S. By construction, every object A in S is equal to f of all the objects less than A in S, where I'm using this notation to refer to the set of all objects less than A in S. Another thing you might notice about these sets is that they are built in a very similar way to the way we were making well orders earlier when we were trying to prove the well ordering theorem. It turns out that each of these sets is well ordered as well. So, in building bigger objects with f, the sets we make satisfy these two conditions. How powerful are these two conditions? Well, consider an arbitrary set S satisfying these two conditions. Because it is well ordered, it has the least element x. Then we know that f of everything less than x in S will be equal to x. But since x is the least element of S, this set is just the empty set. Thus, x is equal to f of the empty set. This applies to any set S satisfying these two conditions, so all sets satisfying these two conditions start with the same object. And it keeps going. Now, think of the next smallest element after x, which we'll call y. The set of everything less than y is the set containing just x, so y is equal to f of the set containing just x. Again, this applies to any set S satisfying these two conditions, so all sets satisfying these two conditions start with the same two objects. In fact, we can continue this argument indefinitely, showing that the sets satisfying these two conditions exactly describe our sequence of larger and larger objects. But wait, aren't we still invoking doing something infinitely in this argument? Well, here's where we can finally work around this issue. Let's completely start the proof over and forget about the infinite sequence, rigorously speaking. Instead, let's focus purely on the set satisfying these two conditions. We will say that a set is conforming if it satisfies these two conditions. While we are talking about these conforming sets to be able to bypass the infinite sequence, it's important to keep in mind that conceptually, these conforming sets still represent the infinite sequence. So does every conforming set start with the same elements? Well, consider two conforming sets A and B. If they don't start with the same elements, because they're well ordered, there must be some least element in each one where they're unequal, so that they are equal everywhere before these points. But we know that these 2 points are equal to f of everything before them, and because everything before these points is equal, the 2 points must be equal as well. This contradicts them being the least elements that are unequal, meaning that our original assumption that two conforming sets don't start with the same elements was wrong. In fact, given any two unequal conforming sets, one must be a strict extension of the other. So what are we doing again? That's right, looking for a maximal element. And we started looking at conforming sets because they seem to describe our original idea of iteratively building a maximal element. However, while the conforming sets are a neat way to represent our infinite sequence without mentioning infinity, they only represent parts of the sequence, not the entire sequence. If each conforming set represents a part of the sequence, and we're looking for the end of the sequence, is there any way to get the biggest conforming set? Well, why not try the union of all conforming sets? Let's call this union C. It's not too difficult to prove that C itself is conforming, and because it contains all conforming sets, it must be the biggest conforming set. In particular, it means that C can't have a strict upper bound. For if it did, we could add f of C to C to get a bigger conforming set, but C is already the biggest conforming set. So what we now have is a well-ordered set C that doesn't have a strict upper bound. In some sense, this means that C is maximal, so we have now proven that there exists a maximal well-ordered subset. It's interesting to note that up until this point, we still haven't utilized the fact that every chain has an upper bound. Thus, we have actually managed to prove that there exists a maximal well-ordered subset in all partially ordered sets. Thankfully, at this point the proof of Zorn's lemma itself is simple. C is a chain, and because every chain has an upper bound, C has an upper bound M. If there was anything greater than M, it would be a strict upper bound of C, which we've already seen is impossible. Thus, M is maximal, and the proof of Zorn's lemma is complete. Well, there's not much more to say about Zorn's lemma, so... Alright, you really want to hear about how it relates to the axiom of choice or where choice was used in the proof? I personally find the axiom of choice to be obviously true and have no qualms about using it, even in situations where it's not necessary, but if you really want to, see if you can find the use of choice in the proof yourself. Anyway, next time you find yourself trying to iteratively build a large mathematical object, I hope that Zorn's lemma will naturally come to mind as a possible tool to use.